Okay, so we're doing section 6 of chapter 2. It is called derivatives of inverse functions. So first off, the derivative of an inverse function, if you know the inverse function, you can just do the derivative of it, but sometimes you don't know all the information, and so this method can save you some trouble. So if f is differentiable and it has an inverse, we'll call it g, then g would also be differentiable, so that f inverse of g does not equal 0. It has to be a qualifier there, or f prime of g does not have to be a qualifier. So if g is the inverse here, then let me change to a pointer. If g is an inverse, the first derivative of g, and g is the inverse of f, then 1 over the first derivative of f, plug in the original g function, the actual inverse, that would be the derivative. So we'll do some examples. But again, if g is the inverse of f, then g prime is equal to 1 divided by f prime of g. Okay. All right, so we will try an example. All right, so we have this function, f of x equals 1/4 x cubed plus x minus 1. What is the value? First thing we're going to do is what is the value of f inverse of x at x is equal to 3? Okay, so that's what it's saying. So f inverse is asking for part A, f inverse of 3. All right, so if you keep in mind, this graph shows us we have our f function, that is this darker bolded line, and then that lighter gray line is f inverse. Okay, inverses do reflect across the line y equals x, so show that line of reflection. All right, so that means my input on my f function is 2 and my output is 3. And that reverses when you go to the inverse, and that always happens. Okay, so when it's asking what is f inverse of 3, I can actually just look at my graph. Here's my f inverse graph. When I plug in 3, I get 2. So we didn't have to really do anything except for use the graph of the inverse. So if you're not given the graph of an inverse and you're not sure how to do the math for it, you can graph it in your calculator and be able to get it. So I know because the input, it tells you the value at x is 3, the output is 2. So f inverse of 3 would have to be 2. One reason that's easier is because solving this for the inverse, if you remember from chapter P, the inverse function, if we were to do that, would be very difficult because we have to solve f inverse. We have to solve f of x, replace all the x's with y's, and replace all the y's with x. We would then have to figure out how to get y by itself when it had a cubed and another value, and it's not factorable, and it would just be too hard. And so a graph in cases like that, when you can't calculate the inverse, would save you some trouble. So now it's asking for us to use the derivative of the inverse, which is this up here, 1 over f prime of my inverse. Okay, so we want to find f inverse, the first derivative of our f inverse. So in that case, you look back at that rule, that would be g, okay, is what it's saying. And so when you do that, it is 1 over f prime of your inverse, and in this case, it's at that specific value. If not, it'd be of x. Okay, so I don't actually have to know what the inverse function is as long as I know the value at this point. If it doesn't give you a specific location, it would probably be an easier inverse to calculate, and you would just be able to calculate it. So what I can do is 1 over f prime of 2, because I know that f inverse of 3 is 2. We calculated that in part A. So I do need to find f prime, and so we'll do a little side over here. F prime I can actually calculate pretty easily. Okay. If I take this 3 and multiply it down in front, I get 3/4 x squared plus 1 is my derivative. And so then I will just plug in 2. So 1 over f prime of 2 is 1 over 3/4. My 4 looks wonky. Of 2 squared plus 1. Okay, which is equal to 1 over 4. So we have this big list, derivatives of inverse functions, and we're going to let u be differentiable. Okay, and we have, there's different ways to write. So if you notice, this is arc sine. That is the same thing as sine inverse. And this would be tan inverse, and this would be secant inverse. And so depending on your textbook or depending on your teacher or your class when you're in college, they'll use those interchangeably. So just keep that in mind when you see that arc in front of it, it's asking you for the inverse. Out of all of these two are going to be your main focus on memorization for the AP test, but you might see other ones and you can just refer back to one of the derivatives list so you can do it. How it works though is if there's a function inside of your trig function, so for example I have arc sine of u, my numerator will be the derivative of that function inside of it, and then my denominator will be square root of 1 minus that number or value or function squared. Okay. All right, so just keep that in mind. And then if you have to chain rule things, you have to chain rule things. So just keep that in mind too. And we'll do some practice problems like that. But you do want to focus on memorizing arc sine and arc tangent. All right, so we'll do some practice problems. So we're going to differentiate arc sine of 2x. Okay, so when I'm using this, I'll refer back to my rule. And my rule for that is u prime all over 1 minus u squared. Okay, so we'll kind of use that as our format. So this is my u in this case. So my u prime, the derivative of 2x is just 2. And then my square root, and this is 1. And then it's my u squared, so it's going to be minus the quantity of my u squared, in this case 2x. So you have to do the whole thing squared, and I can simplify that a little bit so that I have this. That can't simplify anymore. Like I know 1's a perfect square, and I know 4x squared is a perfect square, and you have square root over the whole thing, but that subtraction changes that. So square root, you can simplify parts of square roots if they're products, not if they're adds, or additions, or summations, or subtractions. All right, so we'll do tangent. Okay, so the tangent rule says u prime over 1 plus u squared. So that all my u prime will be 3, because the derivative of 3x is just 3, over 1 plus 3x quantity squared. And that then we can simplify a little bit so that we have that. All right. Think of this u, that's my u, but think of him as x to the 1/2 as we do this. Okay. So we already have sign written up there, so I will have my u prime is 1/2 x to the negative 1/2 all over 1 plus square root of x squared, or to the 1/2 squared. And then if I simplify that, okay, we'll simplify it more than once just so I don't do more than one step in here. So we'll simplify that root in the bottom first. You square root, happens that. So I have to kind of fix the top. So that x has a negative power. Okay, so that x is going to have to go in the denominator. The x to the 1/2 has to go in the bottom. I still have my 1 plus x in the denominator too. So I've moved this guy down because he has a negative exponent. And then I have a 1/2. Well, that 2 is in a denominator, so it stays in a denominator. So you would actually have this of what you have there. You can leave it like that, or you can distribute the 1/2 through. Okay, that would be an okay thing to do too. Oh, I left off the square root. Whoopsie. So you have this. Because they both have square roots though, because x to the 1/2 is a square root and actually a square, you could distribute it through and have the square root of x to the 1/2 plus x to the 3/2 if you wanted to. You could do something like that. But we will leave it like that for now. I'm just real careful. I copied down part of my tangent thing, and those are supposed to be minuses. Okay. And then last one is secant. It's not that secant will ever show up. It's very unlikely to show up on AP test. Okay, be a rare day for that. So if you go back up and look at your secant rule, it is u prime, so my derivative, absolute value of u, and then u squared minus 1. So kind of like sine, but it's switched. Instead of 1 first, it's u squared minus 1. All right, so my numerator will be the derivative of this. So if you derive e to the 2x, it is e to the 2x times the derivative of your exponent, which is 2x. Then your denominator is the absolute value of your u, in this case, e to the 2x, times the square root of my u squared, so e to the 2x squared, and then minus 1. And I can simplify that a little bit. Okay, we'll first simplify inside that square root. So I have 2x e to the 2x all over absolute value of e to the 2x. And actually, let's drop those absolute value bars. Reason being is e to the 2x will always be positive, because even if the x in the exponent is negative, that takes it across the y-axis. It doesn't drop it down below the x-axis. So since e is always positive in this case, there's not a negative in front of it, that whole thing is going to be positive. If you're not sure, graph it. But an e function looks like, trying to write with an eraser, looks like this. Okay, across this, it's not ever negative. And so unless you multiply by a negative in front of it, it's not going to be. And then I have my square root of e to the 4x, if I square that, minus 1. You just multiply when you square things, so don't square that x in the exponent. If you notice, there's an e to the 2x on top and e to the 2x on bottom, so it simplifies one more time to be 2x all over, which is 2. Just 2, because the derivative of 2x is just 2. Square root of e to the 4x minus 1. So you just have to use those formulas very carefully. All right, so we'll take it up a notch. So we're going to combine some concepts. So we still have our arc sign. Okay, so we'll use the rules we've been doing. And then we have this, which is just a product. Okay, so we'll use our product rule and chain rule. So dy over dx is equal to the derivative of arc sign. This is your u, which is nice. The derivative of x is just 1 all over. And then you have your square root. And you have 1 minus your u squared. And that doesn't even simplify. So it's really pretty, really, really nice. All right. Then we have plus, and we have to product rule this. So we're going to have 1 d2, and which I'll think of this part over here as 1 minus x squared to the 1/2 power instead of square root. So times, and we're going to derive our second part with our chain rule. So the inside stays the same, but the outside got the derivative. So I multiplied the exponent in front and subtracted 1 from exponent. And then you have to multiply by the inside. And it'll be negative 2x. All right, so that is 1 d2 plus 2 d1. And the derivative of x is just 1. And you don't even have to write it. Okay, so we have this. So let's simplify it a little bit. All right, let's go ahead and keep this fraction for now where it's at. And then let's work on this fraction here, because I have a negative exponent, so I know my fraction. So I know that 1 minus x squared, and it's going to be, let's go ahead and put it in a square root, since it's going to be the denominator, because if you notice the one to the left has a square root denominator. So that is this term moved down where it's supposed to be. And then this 2 and this negative 2, okay, the 2's will cancel, leaving you with just a negative. And we have this x and this x to combine. X times x is x squared. So we have this. So it would be a minus. Okay, so instead of having plus a negative, let's go ahead and change it to a minus so we don't lose that negative. And then we have plus the square root of 1 minus x squared. But in order to sake of simplification, let's put it over 1 so that we have everything written as a fraction. So if you notice, our denominator on the first two match, but the last one doesn't match. But it'd be easy to make match because I can multiply top and bottom by 1 minus x squared. And then they would all have that matching denominator. So that my numerator is now 1 minus x squared plus, when I multiply that, the same thing times same thing. So it's technically square root of 1 minus x squared, and squaring a root or multiplying by itself with a root cancels, and I'll have 1 minus x squared here. And my denominator is square root of 1 minus x squared. And that will simplify a little bit, because if you notice in the numerator, I now have 2 minus 2x squared over 1 minus x squared. And I can actually factor that 2 out, and you should, because that leaves me with 1 minus x squared, which is familiar because that's also in the denominator. But actually, I'm going to erase that root because remember, that root also means this, correct? So I have one full 1 minus x squared on the top, and I have the square root of that on bottom. So I have one of them on top and half on bottom. So if I use the fact that those are similar terms and I'm to simplify, one on top, half on bottom, I'm left with half on top because you subtract exponents when you, so I have that. So you can leave it like that, or you can write it as 2 root 1 minus x squared. That's kind of up to you. So we kind of combined our product rule and the new inverse rules. That is actually the last example. But here's another summary. So you had a summary on one of the previous sections of derivatives. Here's another summary that is just combining everything you know. And it's on page 185 if you ever need to access it for your homework or put a sticky note in it so you can see it. But if you're can't remember a derivative rule, you might flip to one of these pages that has all your rules put together for you to use. And just keep in mind when you are memorizing like the sine and tangent of these new rules, those are really, really important.